Welcome to my presentation of Lab 2, Motion of a Falling Object. In this lab, we will observe an object's motion as it falls from rest and create two models, one that simulates only the effect of gravity on the object's motion, and another that simulates the effect of gravity and drag on the object's motion. The purpose of making these observations is to use Newton's second law to show how a non-zero net force acting on an object affects that object's velocity and its motion. Moving over to Tracker, we can see video of the observed motion. The ball being dropped is a ball with mass 180 grams. The origin has been created as the center of mass of this ball at its initial position, and the axes have been tilted slightly to follow the ball's center of mass as it drops. The ball will be dropped from the origin downwards in the negative y direction, which can be seen now. On the right side of the screen, the negative y values confirm that the ball dropped in the negative y direction, as they are all negative. On this position versus time graph, we can see that there's a changing slope, meaning the ball's velocity was changing throughout. This makes sense, as the ball dropped, the force of gravity caused the ball's velocity to increase over time. We now move over to Python to examine the creation of our first model. This model accounts only for the force of gravity acting on the ball, as can be seen here, as Fnet is set only to W, the weight force. W is calculated as the ball's mass times the gravitational force, 9.8. We can see here that Newton's second law has been entered here to predict the motion of the ball as time goes on. This says that the ball's final velocity is equal to its initial velocity plus the net force, which is only the weight force, divided by the ball's mass times delta t. When we run this code, we get similar results to what we observed in Tracker, and we see here that the ball drops straight down, and the only force acting on the ball is this yellow arrow, which represents the gravitational force. On this graph, we see the predicted motion of the ball plotted against the actual observed motion of the ball. As we can see, the model has predicted the ball to fall further than it actually did. This makes sense, as the model accounts only for the gravitational force on the ball, while the ball actually experienced forces due to gravity and drag. To account for this, we'll create a model that includes gravitational force and drag force. The second model is very similar to our first model except for a few key differences, the main being that the calculation of Fnet, the total net force acting on the ball, is now calculated as the weight force plus Fd, which is the drag force, which is calculated as negative b, the drag force proportionality constant, which has been calculated to be 0.1067, times the magnitude of the ball's velocity times the ball's velocity. When we run this code, we see that the results look similar to our previous model except for the addition of this blue arrow, which represents the drag force acting on the ball. When added to the plot we looked at earlier, we can see that the line from this new model in yellow matches the observed motion almost perfectly. This is because the addition of the drag force has slowed the ball down and caused its final position to be lower than that of the ball which did not have a drag force acting upon it, which was represented by this line in our first model. Now that we have our two models and we can see how changing the net force acting on the object can change its motion, we can answer a few questions. Which of these models predict a terminal velocity? We know that terminal velocity is the constant velocity the object reaches when the gravitational force acting on the object is equal in magnitude to the drag force acting on the object. Since the first model has no drag force, the model does not predict a terminal velocity. This is because the ball's velocity is always increasing as it's falling, due to the only force acting on it being the gravitational force. The second model appears to reach a terminal velocity right around this area as the slope looks constant, but upon calculating its velocity at several points within this time interval, we see that its velocity is in fact still increasing, although it's increasing at a slower rate as time goes on. This suggests that not enough time has passed to allow the drag force and the gravitational force to come into equilibrium, but had we observed the object for a longer time, we would in fact see it reach its terminal velocity. And the last question, If the object was initially thrown downward, would the terminal velocity be the same as if the object were dropped from rest? Well, had the ball been thrown downwards instead of dropped from rest, the drag force would simply cause the ball to decelerate until it reached its terminal velocity, at which point the drag force would be equal in magnitude to the gravitational force and the ball would fall at a constant velocity.